All right, eyes up here in 5, 4, 3, 2, 1. All right, so most of us had said we had completed through number 3, and I was going to go in order from easiest to hardest. So I'm starting in the middle. Give me a thumbs up if you got your balanced chemical equation. 6, 2, 2, 3. A lot of us look good there. It did take a second because you had to realize you had 3 on the chlorine, so if that's from crisscrossing your aluminum charge, so that's 6 chlorines. The only way you're going to get HCl to have 6 chlorines, put a 6 in the front. So I made 6 hydrogens. So then you say, I need 6 hydrogens, so you put a 3 in the front there. And then because of the 2 aluminums, you already have your 2 aluminums. Your favorite piece of aluminum did single replacement and made hydrogen gas. Okay, so these are all your givens, and I'm sure you made it at least that far. What was the first thing you guys chose to do? Yeah, it's number 3. Okay, so we changed them all into units that would be correlating to our value for the ideal gas law. So our value is 0.0821 atmosphere liters per mole K. And I'm just going to tell you this caveat real fast. There are probably 4 R constants out there in the world, and they all correlate with different pressures. So kilopascals, millimeters of mercury, torr, there's the R constant with like rate of effusion, which you guys saw in a couple of things. Why do I stick with this one? Because it keeps you really focused. Because if I throw 14 R values at you, sometimes you guys don't think enough to make sure you're using the right one. So I'm giving you this one always, and I'm making us always convert these to correlating units because it makes your life so much easier if we stick with one method. Because sometimes it's hard enough to learn one method, not even 4. So on top of that, yes, go ahead and convert this to what? Great, and you guys can do that in your calculator. What's your atmospheres here? 0.9576, something like that. What'd you say?
0.976.
Okay, I'm gonna William say that one more time.
0.9476.
Thank you. I'd like to hear a bunch of people at the same time. Okay, and then here we're gonna take 273, and that is what? Okay, and everything else is hunky-dory, right? So, knowing this, we're already talking about the fact that we have aluminum in grams, and then we have to find the V. We have to find the theoretical yield of hydrogen gas as a volume. What variable are we going to be solving for first, then? Say again? Well, can I solve for V right now if I don't have everything for the ideal gas law? No. So I have P and T and R. So what else am I missing? N. So my true question first is, what is N? Well, N has to be referring to moles of what? Has to, yeah, if we're using the ideal gas law, it's not ideal metal law, right? It's the ideal gas law. So you have to take your aluminum and convert it to what? Moles of hydrogen eventually, right? So let's go ahead and take this right here. I'm going to kind of do a little stoichiometry. So 6.2 grams of aluminum. First step was what? 1 mole of aluminum weighs, thank you, so that gives me 2 moles of aluminum, and I'm going to keep going here, so I'm just going to go down here. So my grams and grams will cancel, and then my moles of aluminum, I need to get to what? And what's our relationship there? 2 and 3. So yeah, 3 will go on top because of what? Canceling units, right? So 3 moles of what? H2 gas, and that's 2 moles of aluminum bottom, and that will show the cancellation of moles of aluminum and moles of aluminum. Okie dokie. So that's like 0.3446. Can I get a second on that? Something close? Okay. Okay, so this is N. Alright, so do I have everything now for the ideal gas law? Sweetly. Okay, so we're going to solve for what now? We're going to solve for what? V, volume, right? So solving for V means I have to isolate V, which means I need to divide by P on both sides. Okay, and so that's V is equal to nRT over P. So what's in my N for my moles of gas? 3, 4, 4, 6 moles. What's my R? Atmospheres times liters per mole. Okay, I'm really not sure what that formula is for. Surprise. Okay, and then temperature? 295 Kelvin over 0.9, what was that? 476 atmospheres. What units cancel? Everything except for liters. It should anyway, right? So those are moles on top and bottom. Wonderful. Kelvin, bottom and top. Wonderful. Atmospheres, top and then like bottom. Wonderful. Liters remain. A lot of you guys are doing a really good job on I was looking at your problem set. I was really happy with most of your problem sets. They look fantastic. A couple people use Celsius. It was like 2 questions. You just got to make sure you're straight with Celsius. It doesn't get used in gas laws. The only 2 that were concerning me were 16 and 17 because those were actually like this. They required you to write a reaction and then think about, am I in a gas? Well, no, I have to convert to moles of gas and then use the stoichiometry before you use the ideal gas law or vice versa. Solve for your ideal gas law and then use your stoichiometry to solve for moles of metal or something. So you guys did really well on that. Some of your balance chemical equations were looking pretty good. Okay, so what's our volume here? You guys got to calculate for me. Say again? Okay, liters. And how many sig figs should this truly be recorded in? Going back to our givens. 3. This one has 4. This one has 3. This one has 3. This has, okay, well that's not used yet, but we're going to have 3, so that'd be 808.81 liters. Okay, so this is my what yield? Theoretical yield. This is like, if my my aluminum perfectly reacted all the way, and that aluminum 100% reacted with the HCl to make that gas, that's how much gas I would make. That's how much gas I would make. But what did this person collect? 7.2. So how do I do percent yield? Actual yield over theoretical yield times 100. Okay, so actual is 7.20. Yeah, theoretical is 8.81. And times 100, what's your percent yield? Say again? Say again? I'm going to round to 80. Well, 81.7 is good. You don't have to round. Can I get a second on that? Yes? I got one person to me. Okay. All right, so out of all of those, I know this was like the medium easy one from the stoichiometry perspective. Do you get this? Do you see the reaction correlating with the gas law? And then the fact that there's some math that's involved before we can plug into the gas law itself because we just didn't have a gas yet. Most of these problems will either have do your gas law first and then do stoichiometry at the end, or stoichiometry first, gas law at the end. Okay? So between 4 and 5, which one do you guys want to do right now? I see 5. Any others? Any other votes? I love a good vote here. Can I get more than 4 people in my survey? Sure. I see mostly 5s. Okay, so thanks guys. You got to use your rights to vote. But here we go. I'm going to take this up after this, so make sure you have all your work on there. All right, so you guys remember from question 4 when you were a good citizen, you were watching that Earth Day documentary that was this weekend? Yeah. So you're watching on Netflix all about acid rain, and you learned a lot of stuff from that. So you also learned that ammonia-based fertilizers, they pollute the ocean. It's called eutrophication. So I tried to embed some other fun facts in here for you. The Haber process, which is N2 plus H2 yields NH3, and it says plus heat because it's going to just try to give you some some enthalpy definitions here. It says this is unbalanced. Balance it first. Syrian.
In 2 slides, you get 3 hydrogens.
Okay.
And there's 2 ammonia.
Beautiful. Okay, so
4 heats.
because there's what?
4 heats.
Oh, you don't know how many heats there are. Do you? It'd be weird if you did. But I don't know how many heats there are. Okay. So we have this fertilizer and it's making heat. So you wonder, just wondering, you're scratching your head, is this endothermic or exothermic? Everybody. Why exo? Because it's putting out heat, right? This shows that it's an exothermic reaction because it's releasing heat, and that's something that we're going to start to talk about now with thermochemistry as we get along with that. So if 170 grams, this is me just writing down the givens, nothing special, grams of ammonia, which NH3 is ammonia. What's ammonium? NH4 plus. Yeah, it's a cation, so you make sure you say charge too. Then how many grams of nitrogen gas are needed? So if I have this many grams produced, how many grams of nitrogen gas are needed? Pause there. I'm not going to go to the second question just yet. That's all I have to work with. Don't even read the question again. What do you have to start with? Hold on. You have to start with what?
170.
You have to start with 170. That's the only number you have. You can't start with a question. And then, Syrian, what do you do next?
Then you get the molar.
What's the molar mass?
Which is 1 mole over.
1 mole over 17.034 grams. So this is old school, right? We're just taking grams to mole, that's molar mass. Where am I getting this number from, Syrian? Periodic table, adding it up. Somebody other than Syrian, tell me where I'm going from there. William, wonderful volunteer.
When you're gonna take 1 mole of N2,
Why 1 mole of N2?
because when you look at, we're trying to figure out how many grams of nitrogen you have. So if you look at your mole ratios from the chemical equation, you see that you have 1 mole of N2 for every 2 moles of ammonia.
For every 2 moles of ammonium. Okay, or ammonia. Okay, good. So stop there for a second. So first of all, I'm doing number 5, but number 5 was easier than number 4. Just saying. Okay. So I mean, easier than basically easier than 3 and 4. But you guys asked for it, so here we go. So you're taking your grams, you're going to moles. You're going from moles of the thing you have to the moles of the nitrogen that the question was asking about using what? Balanced chemical equation, mole ratio. That's where our coefficients are coming in, and that's where this 1 and 2 came from. And then Jacob, what would you do last to get to your final answer here? Look at the answers requested units. What's the question asking for? And where am I at right now? So how do you go to the last step? Put 1 mole of nitrogen on the bottom, and which is, look at the periodic table, it's right in front of you. You guys like to guess. I think it's like 2. That's just plain old nitrogen. 28 grams per mole because it's diatomic nitrogen. Okie dokie, artichokes. What's 170 divided by 17? That's about 10. Divided by 2 is about 5, and then 5 times 28 is like 10. Yeah, please. 10. Oh, 139. Wait, what? How many sig figs should this have? 4. 139.8 grams of nitrogen. Okay, so that's question A, I'll say. Now, question 2. How many liters of nitrogen gas is this, assuming STP conditions? So stop. What comes to mind when you hear STP conditions? 22.4 what? Per mole. What do we have right now? We have grams. So can I use it yet? Nah. Okay, so I got to take this and do what? Convert it back to moles. So convert it back to moles. And Sophie, help me out here. How do I convert back to moles? So the 28 grams that Jacob told us earlier. And on top? And then Mikado, finish it up.
We then go to 22.4, right?
Where do I put that?
You put it on top.
Because it's referring to what unit? Liters per 1 mole of this said gas, right? Remember, you can only use 22.4 at STP, and it has to be talking about a gas, which nitrogen is a lovely gas. It's most of our atmosphere. So that was like 5, it was like 100. Yeah, 111 point what?
8.
It's fine. And that's going to have how many sig figs? So it'll be 1.
4 sig figs?
No, sorry. This one. That's going to limit us. Truly, because we don't have any more sig figs there.
Wait, isn't that
It's a constant, but this is actually accurate to the conditions of STP.
Okay.
Not often do we always refer to our constants like our conversion factor, but this is a condition contingent upon the conditions of the problem STP. So I would round this to 112 liters. If you put the other one, I get it. On CK12, though, it won't let you get your correct sig figs. I'm sure you can figure that out now, okay? All right, so I'm going to stop that for now. We have a little bit longer in class. So where's my telephone? All right, so we have 25 minutes left in class. Here's what I'm going to do. Between today and tomorrow, we're going to finish this introduction to heat. Introduction to heat does require us to kind of take a look at some information we already know, but I want to show you where to my website. And from there, I'll kind of give you some freedom to choose which one you want to use. So go back to my website. If you have your computer out, somebody at your table should at least have their computer out. I'm going to take those worksheets up, so in a moment I'll pass on the stapler, staple this to that, so I'll get that from you, because I'd like to give you as much absolute free credit as I can on that, because you guys worked so well. Fantastic, even.
It's really hard.
No, I said 5 was harder than 4. I didn't say 4 was hard. I just said 5. I mean, 5 was easier than 4. Yeah. It's all stoichiometry. I just didn't make you do a limiting reagent off the bat, except for on homework. All right. So on my website, Caleb, are you on my website? Yeah. Caleb, are you really on my website? Okay, that's not my website. Okay, so you're at the. You guys know, just Google Jessica Inlow, and I'm like the first one that comes up. Or Jessica Inlow Cox Mill, and it'll be the first one. So Unit 6, go under Unit 6, and so we're basically moving away from gases and states of matter into thermochemistry, but it all relates to energy, so they start to kind of mesh together some. So that's why I'm not testing you right now, because I feel like after knowing that CK12, you have successfully mastered that, and then this right here, I can see where some mistakes fail. I can actually give you a mastery grade based on your attention to the details that I was requesting. So under here, if you go down to Unit 6, it says Thermochem WebQuest Final.pdf. Yeah, that's real specific. So when you click that, that's going to be what you start today. You will likely have to finish tomorrow, because I know tonight I have you reading 2 close readings. One is really short. What's the first article called? Does cold exist, right? And the other one is about ice packs and hot packs. The first one's pretty short, so I'm having you guys read those collectively together, because tomorrow you're going to come together and do kind of a worksheet related to both those readings. So you're not going to do the share and pair and share thing. You're actually going to be talking to each other about what you read, but not really giving new information to each other. So here it has you do a little background reading first on what is heat, and it should be somewhat familiar to your Reading Guide 17, which is why I gave you Reading Guide 17 back, so you can always play back and forth between this and your Reading Guide 17 and answering those questions. Now this one makes you go through and actually manipulate some equations, and this is the one that I always have to help people on down here. So get as far as you can, and then when you're like, oh my gosh, I need help, I'm probably going to do that tomorrow with you guys, so just get as far as you can and then move from there. Section 3 I'm sorry, the after section 2, it gives you a lot of reading related to the equation that you were speaking of from this morning, so you might even see some very familiar items. Down here is where I probably will have to help you a little bit too, according to the calculation of specific key. So don't fret. Like, do try to get as far as you can, and good test-taking skills means you move on if you don't know something. After that, it has some heat curves. It makes you describe what's happening, and this is like actually you listening or watching this little simulation, and then there's a couple of ideas about endothermic and exothermic you'll answer. So I'm giving you about 25 minutes now, and about 25, 30 minutes tomorrow to finish those up. The thing that I think you should probably address tonight, so you don't have to do it this weekend, especially if you're going to prom, is part 5, which is about 15 things in your home that you could change to be more energy efficient. 15, yeah. So some of them are going to be quite easy for you to find out immediately, but if that's something you don't want to have to think about over the weekend, think about it like kind of throughout the day. Okay? So if this is something you would like to start now, start now. If you're like, I need to do CK12 because I know I'm not going to do it at home, do CK12. Go.
CK12, like an actual assignment.
Mm-hmm. Yeah, and it's due on Monday.
Just the
states and gases one. The other ones I have due dates on for Friday, but I can change those due dates with the stoichiometry side of things. Put them on the back side. Guys, listen up. Let me give you one more hint here, okay? So this is your reading from that I handed you yesterday, right? This is just one article, why cold doesn't exist. And then when you staple it, and I'm passing around stapler now, the second one's like, it's all together now, starts over here, hot pack, and then do you see the picture connects in the middle? That actually, that does go together. So that's that, and then it has you reading a little bit more about entropy. You'll find some of these things are very familiar to you already. I'm passing on stapler now.
I just highlighted.
Summary reflection. One summary, one reflection.
Per article?
One entire, one entire. I'll write that down.
I don't remember. What is it? A 2-sentence summary.
I got you. You just watch. Hold on. I actually put the whole guide there. Because I was like, people are going to be like, what am I supposed to do? So, it gives you some information, close reading, annotations, and that's 6 points worth, so be very thorough. Summary statement is 25 words or less, and the reflection is just 1 to 2 sentences. And this says to use a couple of these things, like I wonder, I think, I realized. Those are just interesting stems. But this, I told you guys just to have rich comments, and I'm happy. Okay? Rich comments.
When I'm forced to why? I sit down to annotate with him, like I'm just like writing down his words and saying, that's what I should add with it.
Well,
Alright, I like this.
I like the long things.
Yeah, I work in my armor sword, and I use a hot pack. Ooh, yeah.
Release the energy in here, really.
Guys, I love you to death. Some of you guys are using your time super wisely, and some of you guys are not. So, impress me. This is end of class. It's a little bit messy. Yeah.
So it's like one summary.
Just one collective summary.
They're both really related.
Yeah, I'm on myself.
Now, one reflection. I want you to
Jesus Christ.